Hello, in this particular lecture we're going to have a look at some of the important principles behind architectural design. These are somewhat abstract, but they're ones that apply quite generically to most software systems. And certainly for the type of architectures that we're trying to design for our games, these the principles we'll have a look at will be quite important by way of helping you get a design that is flexible, maintainable, and the type of thing that's going to score well within the module. So we'll start off by identifying which of the design principles we will explore. We're only picking a selection of some of the more popular ones. It's an incomplete list. There's an awful lot of additional detail that potentially could be added in here. And for us, the focal point that we have is the desire to develop a good object-oriented design, one that fits well for the game that you have, one that's flexible as you extend or enhance the game, one that's also easily maintained, so it's the type of thing you can go in, you can tweak, you can modify. For us, the principles that we'll have a look at are going to be the notions of cohesion and of coupling, and then the S.O.L.I.D design principles. Start off first of all then with cohesion and coupling. So they're sort of related concepts that sit nicely alongside one another. By coupling, what we mean by this is the extent to which we have a class, or it could be a component, it could be several different classes, the extent to which it's tied into other classes or other components. So if we say something is tightly coupled, what we mean by that is that if I wanted to lift out, for example, your class and to use it in my own program, if it's tightly coupled with other classes, then I also have to bring them with me as well. I can't simply pick out your class and use that. Your class won't work without the other classes. And depending upon the degree of coupling that they have with other classes, you can very quickly get yourself into a position where trying to remove one class means that you're bringing large swathes of the system or other classes with you. So ideally, we don't want to have things that are tightly coupled because it limits the reusability of our system. Things that can help improve the coupling, to have not as tight coupling, is through the use of interfaces. If we link our classes or our components together through defined interfaces, that gives you a breakpoint. It means then I could potentially lift out your class and provide my own implementation of whatever interface that it has, and then insert that into my own particular project. So where possible, we want to avoid tight coupling, use interfaces where we do have clearly defined boundaries. A little aside, in terms of games, often it's not always as straightforward as that. If you are connecting two classes through an interface, then there is a performance hit associated with passing data through that interface. So sometimes within games you would go out of your way to tightly couple things together for performance reasons. Related to coupling is the notion of cohesion, and it says here, the extent to which parts of the system are related and work well together. What this means is if you had a class, the class would have high cohesion if all of the methods and the properties that class exposed sit well alongside one another. They all support one another. They form a cohesive whole. So this is very much that the sum the whole is greater than the sum of the parts. Where we wouldn't have high cohesion is if you had, for example, let's say it was a collision detection system within the game, and you had one class that provided some types of collision detection, you had another class that provided another type of collision detection. There you're taking what is a coherent chunk of functionality and spreading it across multiple classes. That potentially lowers the cohesion of it. Equally, if I had a class that some of the methods did this and some of the methods did something different, and the two are not really related, that class isn't particularly cohesive. There's different functions within it. So we want to try to make sure that our design for our classes, for our components, that they have good cohesion, they make sense as a whole when we look at their constituent parts. They all fit together. The other bunch of design properties we're going to look at is what's known as the S.O.L.I.D design principle. There's 5 of them. Unsurprisingly, one begins with S, then O, then L, then I, then D. So we'll have a look at the first one first of all. So the S of S.O.L.I.D stands for Single Responsibility Principle. And it says that one class should have one and only one responsibility. And then that sort of goes at odd end of the picture here of the Swiss Army knife, which has loads of different pieces of functionality. So ideally we want to design our classes so that they have a single piece of responsibility, and we want to avoid classes where one class does one thing and it also does another separate thing if the two are not very closely related in terms of having high cohesion. Why do we want to do this? It improves reuse, it improves the ease of maintainability, it makes it more easily to extend it because each class has a fixed, defined and well-defined role. The O stands for the open-closed principle, and this says that software components should be open for extension but closed for modification. And what does that mean? It accepts that if you develop a class, other people may want to come in and to build upon that particular class to enhance or to change or to modify the behavior. And when we say that software components should be open for extension, what that means is that if I do want to be able to change a class that you've written, I should be able to do that by overriding the methods you have exposed within that class. That should be the mechanism whereby I can tweak and refine my implementation of it. I shouldn't need to go into the class and start changing the code within it. It should be closed for modification internally. And designing things in that way, again, it enhances the extensibility, the ease of maintainability of our classes. The L stands for Liskov's substitution principle. It says there that drive types must be completely substitutable for their base types. What does that mean? Like the example at the bottom, if it looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. And what the substitution principle gets at is that if you do introduce a drive class from some base class, you should take care to make sure that you can always use your drive class anytime the base class would potentially be used. So your drive class should be entirely substitutable for the base class. And what you want to avoid there is putting in additional requirements or assumptions, for example, the need for batteries, where the base class didn't have that particular limitation and that particular requirement. So it's important to make sure you're designing things in that way. The I stands for Interface Segregation Principle. So there we're saying that clients should not be forced to implement unnecessary methods which they will not use. This ties into interfaces. Interfaces have been identified as a good way of improving the degree of, making sure things are not tightly coupled, they're loosely coupled, helping us to improve maintainability, flexibility, and a whole host of positive things. So if we are using interfaces, we should make sure that for our interface, we're not forcing the user to implement a lot of methods that he or she would not want to implement. So if your interface has, for example, 10 methods, and I'm using it, and I only really want to use 2 of them, you don't want to force me to implement the other 8. And that comes down to how we design our interfaces, that the methods or the functionality set out within that interface, the user should see, yes, that this is important, useful, complementary functionality. And in the case of sort of implementing 2 from the 10, assuming I'm not just being lazy, assuming there are good reasons why you only would want the 2 on its own, that's really suggesting you'd have a separate interface for that and not grouping a big bunch together into a larger interface. The final one we have, the D, is the Dependency Inversion Principle. And And it says you should depend on abstractions, not on concretions. And what this is really talking about high-level systems and low-level systems. And again, the image maybe gives a good introduction to this, that would you solder a lump directly to the electrical wiring in a wall? So the lump here is our high-level system. And high-level systems, they very often depend upon low-level systems to work. So they're sort of the component things that go together to provide the functionality that the high-level system works. In the case of a lump, we need something to provide the power for the lump to work. Now, it wouldn't appear to be good sense to solder the lump directly into the wiring, but you know, in quite a lot of software systems, effectively that is what happens. That the high-level system is very much tied into the low-level systems. It can't work without those low-level systems, and it makes a set of assumptions about which low-level systems it is using. Instead, if you were to design it, say for example with a plug, that means then that you can plug your high-level system into any low-level system that provides a suitable interface or suitable socket for it. So this is getting into the design of high-level and low-level. Assuming there's no performance issues, make sure that you are designing your low-level systems to have a nice interface into the high-level system. That improves the ease whereby we can modify or extend or enhance our functionality. So we have some key takeaways on this. Good design, it's underpinned by a reasonably small number of fairly sensible design principles. You can listen to all of those, and there's many other ones, and you think, yeah, they make perfectly good sense, and they do. However, and this is where practice is nowhere near straightforward as theory. If we're actually thinking about our own designs, it's rare for there to be one truly optimal design that is much better than every other design. Quite often there are lots of designs that are sort of a similar level of quality. And a lot of the design principles, they're not necessarily complementary of one another. Sometimes you can have a design which scores particularly well across a few or a number of the principles, but not so well against other ones, and vice versa for different designs. So simple theory, but don't expect the application in terms of practice to be straightforward. And very often you're trying to pick something that maybe gives the right balance, or at least hits a number of the design principles, and certainly avoids any of the negative side in terms of the design principles.